Hi students, welcome to this video, and in this video we're going to be covering 8.3 and 8.4. Now before we start, I just wanted to show you your teams. So Year 12 Chemistry, I click on that, you can see that I've posted some stuff. If you go into your grades, you can see the work that I expect you to complete. So you've got holiday homework week 1, week 2. I have not updated this is not accurate. If you wanted to see what the week 1 coursework was, you can see it from here. And if I receive it, I'm just going to give you a 1. So I'll give you a 1, so Catherwick gets a 1, and then hopefully you can keep track of it. Something else you can do to make my job a bit easier is you can also submit through Teams. So if you wanted to submit your work, instead of sending me the file through Zuno or Teams, just attach the file to your assignment. So over here you click on View Assignment and you'll be able to submit it because, okay, so let's begin. We've already gone through these 8.3, but I don't know if I touched on these tables. If you haven't, if you weren't here last time, you can watch 8.1, 8.2, and 8.3 on Microsoft Teams. So that was just up here. Let's find it. I'll just quickly show you. Up here, this meeting. Okay. So just pay attention to this, and 8.3 says that in the value of the equilibrium constant, if it's between 10 to the negative 4 and 10 to the 4, it indicates that a significant reaction occurs. If it's above 10 to the power 4, it shows that there's almost a complete reaction. In equilibrium, it's never 100%, and if it's less than 10 to the power of negative 4, that means that hardly anything has happened. And this makes sense because our equation is K is equal to the products divided by the concentration of the reactants. Okay, so if the products is a big number, it's going to give us a big equilibrium constant, which makes sense because it'll fit into here. If the reactant is a big number and the products is a small number, it's going to give us a really small number, this really small equilibrium constant, and that means no reaction has occurred because we've got a lot of reactants there. Something else that's important is in an exothermic reaction, if the temperature increases, the equilibrium constant will decrease. In an endothermic reaction, it will increase, and vice versa. So exothermic, temperature decreases, then equilibrium constant will increase, and endothermic, it will decrease if the temperature decreases. Okay, let's begin. So this is question 8.3. This is the one of the ones that you had to do, and it asks about this chemical reaction, and here's the equilibrium constant. For each equation, calculate the value of K at the same temperature, and here it is. So I'm going to label this equation 1, and this can be equation 2. Now let's work out the equilibrium constant for equation 1. So it's the products divided by the reactants. And we know that the equilibrium constant is 1.70 and the units is mole. Now let's just quickly focus on why the units is molar, sorry. So we're taking this equation. This is all in concentration, so you've got M times M, because molar is the unit for concentration, divided by M. Now this cancels out, and you just get M. Now let's go to equation 2. What's the equilibrium constant? Well, it's exactly the same, but this time it's all to the power of 4. Now I just want to make it clear why it is to the power of 4. I just want to get rid of that, because where does this 4 come from? Cl2, it actually comes from here, Cl2. This one comes from here. And that 4, that does not exist yet, it will be from there. And so what does that equal? Well, how can we turn this into this? We can put it to the power of 4, so 1.70 to the power of 4. Let's also do that with the units to the power of 4, and that will give you 8.35 molar to the power of 4. And that's the answer. Okay, let's move on to the next question. Question 5. And it's asking you to state whether the equilibrium constants for each of the following would be increased, decreased, or unchanged by an increase in temperature. So this relates to this table. So let's put this table here and let's have a look. Is this reaction endothermic or exothermic? Well, this reaction is actually endothermic because there's a positive sign. Look at this here, positive. So it's endothermic. Does the temperature increase or decrease? It increases. And so what happens to the equilibrium constant? It also increases. So we know that this reaction is endothermic and the temperature is increasing, therefore K decreases. So the answer is decreased. Okay, let's move on to 8.4. So in 8.4, we're just talking about calculations involving the equilibrium constant. And this can get tricky. So we've already learned all the content. Now we're actually doing the mathematical equations. We're applying, and there is a lot of maths to this. So let's just read the question. A 2.0 litre vessel contains a mixture of 0.0860 mole H2, I2 of HI in equilibrium, that's really important, at 406 degrees Celsius according to this equation. Okay, calculate the value of the equilibrium constant. So that's what we have to do. We have to calculate the value of the equilibrium constant. So how do we start this? Well, this is stoichiometry. Remember stoichiometry? That's what it is. So I'm going to write the equation. Okay, they've given me the mole for everything. They've given me the volume for everything. And to work out the equilibrium constant, I have to get the concentration. So let's fill this out. The mole of H2 . Okay, and I just got that all from the question. Now what's the volume? Well, it's over here. It's all 2 liters. Now how do I work out concentration? Well, we know that concentration is equal to N over V. And so I've already done this, so I'm just going to put in the values. So I'm doing 0.0860 divided by 2, 0.124 divided by 2, okay, so now you've got the concentration. Now you have to calculate the value of the equilibrium constant. So what is the equilibrium constant anyway? Let's write it out. Products, and don't forget the 2. Now we can put the values in. Which is going to give me 48.1. What are the units? Well, let's see. We've got m squared over m times m. Okay, cancels, cancels. There are no units in this. And here's the answer. Now let's just make it really clear again. Where am I getting the information from? I'm just going to rub this all out. Okay. So where did I get this from? I got it from here. Where did I get this from? Got it from here. Where does this go? It goes here. And it all relates to H2. Okay, so I just want you to look at how it all relates, and maybe you can do the same for iodine and hydrogen iodide. Let's go to the next question. Okay, so calculating the equilibrium concentration, consider the following. Equilibrium constant of 0.40. Here's the equation. I'm not going to highlight, I'll just put a little dot. An equilibrium mixture contains this, at 250 degrees Celsius. What is the equilibrium concentration of Cl2? So it's asking me to figure out the concentration of Cl2. So to start, as always, we're going to write the equilibrium constant. Let's substitute the values in. So they give us the equilibrium constant, 0.400. We're trying to work out Cl2. They give us PCl5. And they give us PCl3. Okay, so let's now work out Cl2. You rearrange it, and you will get, okay, I hope that you're not going to have any trouble with rearranging the equations, but if you did, I just multiplied both sides by 0.0020, and then I divided both sides by 0.0010. Okay, last exercise I'm going to do with you, and this is the trickiest. So this is quite tricky, and it might take you a while to understand, but let's just have a go and highlight the important information. It gives us the equilibrium constant. We have an equation. And what's the question asking? What is the equilibrium concentration of NO2 in the mixture? Oops, this is the wrong question. We just did this. Okay, let's get the right equation. Be right back. I'm just going to pause you guys. Okay, sorry about that. Now, we've got the question. Let's just read it. Equilibrium is established between A and B at a specified temperature according to this equation. 0.50 mole was placed in a 2-litre vessel. So initially, we only have 0.45 mole of A in a 2-litre vessel. When equilibrium was achieved, so this is at another point in time when equilibrium was achieved, 0.28 mole of B was present. Calculate the value of the equilibrium constant at this temperature. Okay, so there are 2 time points, initially and after equilibrium. And the way we're going to work this out is we're going to write it out. I'm going to put it more to the left. We're going to use ice. And I'll just, ice means initial. This means, C means change. This means equilibrium. Okay, so initial change and at equilibrium. These are all time points. Just space it out a bit more because we're going to need some space. Okay, so initially you only have 0.50 mole of A, and you don't have any B. What's the change going to be? Well, the change is going to be dependent on the stoichiometry ratios. So let's just say that 1 mole is X. So if we react 1 mole of X, it's going to be minus X, and that means 2B will get 2X. Okay, when equilibrium was achieved, so at equilibrium E, 0.280 mole of B was present. So I'm going to write here 0.28 mole of B was present. Okay, that means that 2x is equal to 0.280 mole. 2x is equal to this value, which means that x is equal to 0.140 mole. So we put here minus x is equal to minus 0.140. So what's 0.54 minus 0.14? Well, it's 0.400. Okay, I hope that makes sense. Just have a look at it again. Okay, if you're really struggling, let me know and I can do another example. But it's just important to know, initially you've only got A. At equilibrium, you've got 0.280 moles of B. So what is the change? And the change will correspond to the stoichiometric ratios. And then you have to minus the change from the initial to work out the equilibrium value of A. Now we have not answered the question yet. It's asking what's the value of the equilibrium constant at this temperature. Now we've got this in moles, and we have to change it to concentration to calculate the equilibrium constant. To do that, we're just going to do it the same way we've always done it. A to B, we have mole, we have volume, and now we need concentration. Our mole is 0.400 and 0.140. I got that from over here. Our volume says 2 liters for both. So 0.400 divided by 2, 0.200. And this divided by 2, 0.80. Oops. Oh. No, 70. Yep. Okay. Now, what we do is, I'm going crazy. Okay, so this is not the right value because we're actually taking this value. So it's 0.280 divided by 2, which is 0.140. That looks much better. Okay, now we can write out our equilibrium constant, which is equal to B to the power of 2, because here's the 2, divided by A, which is equal to 0.1402 divided by 0.200, which gives you 0.0980 molar. Okay, and that's it for this lesson. I know the last question was very tricky, but just remember there are really 2 steps to this, and there are 2 tables. So you need to do ice. So this is the first step, and we use ice, and this is the stoichiometry step, and then we work out the equilibrium constant. Now, if you have any questions, I'll do another example, but for now, I'll just leave it here. It's been a long video.